This is 21549A's submission for the 2022-2023 season STEM Research Challenge, the Solea.
In our submission, we will talk about a few different topics like the brief, design process, our prototype, and our research.
This year's challenge needs us to find a world issue and use mathematical features found in nature to solve it.
We started to think about ideas we could use, but we decided to find a design process to structure our ideas in a better way. After looking for a few different types of process, we decided that the double diamond process would be the best option for the project we had.
The double diamond process focuses on four main stages: discover, define, develop, and deliver. In this project, we are going to go through these four stages.
Our first step was to discover the problem we had to solve. We brainstormed a few ideas, and after some deliberation, we decided to tackle the worldwide energy crisis. With gas prices up tenfold in Europe alone, we started to work on ideas to generate energy affordably, avoiding fossil fuels in sight of their prices. Before we picked ideas, we also had to keep sustainability as a key feature in our product, as it would be a large-scale solution.
To further define the issue and add some context, we looked at existing solutions like wind turbines, solar arrays, and geothermal energy. At the moment, they have two main issues: inconvenience for residential areas and investment costs.
With that in mind, we began to look at mathematical patterns in nature that we could use. A few examples include fractal patterns in Romanesco broccoli and the six-fold symmetry of snowflakes.
For our inspiration, we looked at many different plants and animals, looking at how their physical adaptations were mathematically inspired.
We decided to make a product based on the olive plant's unique leaf types. It has two types of leaf, and both move separately to maximize photosynthesis rates.
The thicker sun leaves have more densely packed chloroplasts to increase sunlight absorption, while the shade leaves have less chloroplasts since they receive less sunlight anyways, maximizing efficiency of resource usage. This phenomena is known as phenotypic plasticity.
We also had many more decisions that led to our design, like limiting the tilt of the top disc to 40 degrees for practical reasons, or our reasoning for leaving the very center of the structure uncovered.
With these decisions in mind, we began prototyping and drew a first sketch. The material of the product in the top disc is gallium arsenide, a cutting-edge technology that has extremely high efficiency of energy conversion.
We then used two more softwares, Onshape and Fusion 360, to further render and develop the design.
When we had to decide a name for our product, we thought of Solea, combining the Latin for olive and solar energy.
The disc itself rotates around the pole by reducing the pressure from the internal hydraulics on specific sides, like the animation shows. We enjoyed researching and creating Solea, and we hope that you too enjoyed watching this presentation. Thank you for listening. Our research was taken from sources of educational and organizational backgrounds, ensuring their reliability, and we used some scientific journals to back up other research. Credits to follow.